Stripping down science. The Naked Scientists.
Hello, it's Sunday, November the 14th. Welcome to The Naked Scientists with me, Ben Valsler.
And me, Helen Scales.
Now this week we're investigating the science of shipping. We'll find out how researchers use wave machines to investigate how damaged ships fare on the high seas, and we'll explore ways to make shipping more sustainable.
And we'll hoist the sky sail to find out how a kite could cut shipping fuels costs by up to 60%.
Plus, why happiness is in the here and now, the energy savings of walking tall, and how evidence from Scottish rocks shows that Earth became oxygenated almost 500 million years earlier than we thought. And of course, we'd love to hear from you. If you'd like to contact us through Twitter, you can just tweet at Naked Scientists, write on our Facebook page, that's at thenakedscientists.com/Facebook, or you can drop us an email. Our email address is chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is The Naked Scientists with me, Ben Valsler, and with Helen Scales. Now, first up, let's take a look at some of the week's biggest breakthroughs from around the world. Now, Helen, when are you at your happiest?
I'm at my happiest. Good question. Possibly when I'm in bed still, actually. In the mornings when I can stay in bed and don't have to get up and work. That'd be quite nice.
I see. Well, research published this week shows that we're actually at our most happy when we're concentrating on the job at hand rather than allowing our minds to wander. But oddly, people actually seem to spend most of their time, almost half of their waking hours, thinking about something other than what they're currently doing. Matthew Killingsworth and Daniel Gilbert from Harvard University developed a free application for smartphone users that contacted its users at random intervals to ascertain their happiness, what they were doing, and importantly, what they were thinking about. They asked if they were thinking about what they were currently doing, or if they weren't thinking about that, if they were thinking about something pleasant, neutral, or unpleasant. Now, it's thought that our ability to contemplate events in the past, as well as possible future events, is actually a vital part of the human condition. It helps us to learn, to reason, and to make plans. But this study, which was published in the journal Science this week, set out to see how it affects our happiness. Now, reports of mind-wandering, or stimulus-independent thought, were actually strikingly common in these results. In fact, for 21 of the 22 different categories of activity, people reported that their minds were wandering no less than 30% of the time. The only activity where people didn't report this much mind-wandering? Well, that was the activity called making love. Now, contrary to what you might expect, the activity in hand didn't actually affect how pleasant the daydreaming was. But how does this relate to happiness? Well, by performing a multi-level regression analysis, which is a statistical analysis that can show causal relationships in sets of data, the researchers were able to show that people were less happy when allowing their minds to wander. In fact, even thinking pleasant thoughts was no more likely to make you happy than staying in the moment. Now, you might think that what you're doing is most likely to affect how happy you are, but actually the analysis showed that the activity you were doing itself only accounted for about 4.6% of the variation in mood, while mind-wandering accounted for over 10%. They could also account for the fact that negative mood is known to lead to a wandering mind. Time lag analysis generally showed that mind wandering was the cause rather than the consequence of unhappiness. So it seems that there may be some truth in the philosophical and religious teachings that tell us happiness is attained by concentrating on the moment and living in the moment, but still a wandering mind is a useful one. The authors argue that the ability to think about what is not happening is a cognitive achievement that comes at an emotional cost. Helen.
Oh, good stuff. Well, I think I will try not to let my mind wander quite as much as it does, but since it does seem to do some good. Well, my story comes up now with news that, as many parents, aunties and uncles probably know full well, kids get much more tired out simply by walking around. than us adults do. And now scientists have taken a step closer to understanding why this might be. It's not just that they run up and down more, or that we actually get more efficient at walking as we grow taller, but in fact it's all about having longer legs. Publishing in the Journal of Experimental Biology, Peter Weyand from the Southern Methodist University in the US led a team of researchers who investigated the metabolism and gait of a group of walking volunteers, and they ranged from 5 to 32 years old, and they were between 3 and over 6 feet tall. Well, it's already known that across all sorts of different animals, those that are smaller and have smaller bodies use more energy per unit of mass than larger animals. But this doesn't actually give us a full answer as to why little people use up more energy walking around, and it's more than just a factor of just their different metabolic rates. Something else is going on. Well, Weyand's team monitored the energy used up by each volunteer as they were asked to walk on a treadmill at different speeds, ranging from half to just under 2 metres a second. And what they discovered was that smaller people use the same amount of energy per stride as taller folk. But obviously, with littler legs, they have to take more strides to cover the same ground, using up more energy in the process. So essentially, if you scaled up a 3-foot 5-year-old to be the same size as a 6-foot adult, sounds quite terrifying to me, but if you were to do that, they would actually walk in exactly the same way, revealing that grown-ups don't have a different, more economic way of walking. They just benefit from having longer legs, essentially.
So if the 5-year-old was on stilts, that actually would be more efficient?
They would use less energy, I suppose, although they have obviously got to be able to walk on the stilts and figure out using their muscles in a different way, because the stilt isn't their own body, essentially. But it is all about the gait and the stature. So essentially it is all about how many strides you take to cover a bit of ground. So yeah, if it was a 5-year-old who could use stilts, I guess that would work. But the kind of neat thing that comes out of these findings, not just, it's not just a case of scientific interest, it's actually a good application of it too, which is that they've got an equation now which really accurately calculates the energetic cost of walking, and that could be fed into applications for things like pedometers and treadmills by inputting not just your weight, as many current machines do at the moment. If you put your height in as well, we could now get a much more accurate representation of how many calories you're likely to burn over a certain distance. And certainly from my perspective, this is fantastic, because it means next time I'm at the gym on the treadmill running next to an elegant, tall athlete, I've got a genuine scientific excuse for finding it much harder work, because just like toddlers, us vertically challenged folk use much more energy just getting around.
Well, sadly, I am 6 foot tall, and so I don't have that excuse, and I'm afraid just have to blame it on not being very fit. Previously, we've believed that the Earth's atmosphere turned oxygen-rich about 800 million years ago, and this ushered in the era that made complex life like us possible. But now, new research from Scotland shows that we might have got it wrong, and in fact, oxygen levels increased much, much earlier. Speaking to Chris Smith, University of Aberdeen geologist Professor John Parnell.
We're examining a key stage in the evolution of life on Earth. The evidence relates to a particular group of microbes which have been very successful and very widespread. Today they colonize everywhere from freezing glaciers down to hot smokers in the deep ocean. They rely on reducing sulfate, so these are what are known as sulfate-reducing bacteria or sulfate-reducing microbes. But they made an important advance by getting energy in a more efficient way, which involved making use of oxygen in the environment. So it's as a marker for increasing oxygen in the atmosphere that they are really important in this context.
So we can use them as a proxy measure for when oxygen in the Earth's atmosphere in general increased, and then that in turn enabled more complicated things like us to come along.
That's right. It's important because as oxygen increased in the atmosphere and started to penetrate into the subsurface, this opened the way to complex life, including animals, and for that life to burrow down beneath the surface. So we're looking not just at an evolution of life, but an evolution of habitat as well, and an evolution of behavior, because, of course, as life went beneath the surface, it could then escape predators, etc.
And can you put some timing on this for us? When exactly, looking back in geological history, are we talking about?
Well, it had been thought that this evolution to make use of oxygen occurred about 800 million years ago. We now have evidence from our rocks in Scotland that this occurred at least 400 million years before that. So we're substantially putting back the boundary to at least 1.2 billion years old. The oldest evidence that we have comes from near Loch Inver in Sutherlandshire on the west coast of Scotland. That's at 1.2 billion. And then we have continuing evidence from about 1 billion years old in the Gairloch district, which is also on the west coast of Scotland.
And when you say you've got this evidence, what are you looking for, and what are you actually finding?
The evidence doesn't come from conventional fossils. It comes from what we call chemical fossils. That is, distinctive chemical signatures that are left behind by the microbes. And in this case, it relates to a detailed analysis of the sulfur that the microbes were using to get energy. That sulfur now occurs in the mineral iron pyrite, and that's what we have sampled and analyzed. And we've done that in a couple of different ways. We have done some chemical extractions from the pyrite. We've also used a laser technique on the pyrite. And in both cases, we extract the sulfur out and then analyze its isotopic composition. And it's the details of that isotopic data that tells us that the microbes must have been using oxygen, and therefore that enough oxygen was available to them.
So why did you undertake this study? Because everyone was pretty sure that about 800 million years ago, that's when things suddenly began to change. So why did you then go looking and say, well, is that really the date?
Well, I mean, most of the rocks from this age are from the ocean. But we were aware that we had rocks back at 1.2 billion, which had been laid down in a large lake. So this is effectively a terrestrial environment, and that means that any microbes that might have been inhabiting that environment were much more in tune with what was going on in the atmosphere. And so if there was going to be anywhere where we might find this earlier signature, it was going to be in terrestrial rocks like the ones we had. So that was a good reason to go looking there. And it happens that these rocks up in northwest Scotland are particularly well preserved for their age. So there was a good reason to go searching there.
And I guess now what you're going to have to do is to independently confirm or corroborate this, perhaps by looking at other rocks from other bits of the world of an equivalent age and see if you can see the same signature written there.
Well, in a way, we actually have already corroborated this, because we first of all looked at the rocks at 1.2 billion. These were the ones near Loch Inver. And then we looked at a younger set of rocks, I mean, quite a different set of rocks of 1 billion years old. These are the ones near Gairloch. And they showed us the continuation of the same signature. So we've shown that this is not just an isolated event. We actually have a continuing story.
And what are the implications of it?
Well, I mean, the implications are that we are pushing back the time at which there was enough oxygen in the atmosphere to support the evolution of complex life. Now, it may well be that there was some other event which eventually kicked off the evolution of animals, but what we've shown is that there was enough oxygen around so that the atmosphere was not a barrier to that evolution.
Which is a good thing, at least where we're concerned. That was Aberdeen University's John Parnell talking with Chris Smith. He's published that work this week in the journal Nature. Now, we've been living alongside cats for thousands of years, but it's taken until now to fully understand how they perform one of the most basic of tasks, and that's drinking. All cats, from the mightiest wild tiger to the laziest fat lap cat, drink with a very subtle action that takes advantage of a balance between gravity and the force of inertia. That's the tendency for something to keep moving in the same direction unless acted upon by an external force. Back in the 1940s, an MIT engineer called Doc Edgerton filmed a domestic cat lapping at milk. We've known since then that they form a distinctive shape with their tongues, curling the tip of the tongue backwards so that the top, or the dorsal side of the tongue, is the first to hit the water. Now, writing in the journal Science, another MIT researcher, Roman Stocker, and his colleagues have used high-speed video footage of domestic cats, including Stocker's own pet, that's Cutter, which is a delightful name for a cat, along with a range of big cats from local zoos. They've used data from these observations to make them able to build a robotic version of a cat's tongue and really get to grips with the mechanisms involved. Now, when the tongue comes into contact with the liquid, some of the liquid will adhere to the surface of the tongue. As the tongue is retracted, it pulls a column of liquid along behind it. And here's where the elegant physics comes into play. The column is pulled up by inertia and simultaneously pulled back down by gravity. At the perfect time, the cat closes its jaw, taking in the tip of the column whilst keeping its chin dry. Now, on average, this is only about 0.1 millilitres of liquid. If it closes its jaw any later, the column would break and it wouldn't get any water, but any earlier and the cat would get a faceful. For larger volumes of water, the balance, this ratio, will be a bit different, and what we see is that big cats, who obviously lap more water at any one time, lap at a different frequency. Interestingly, things like surface tension and viscosity of the fluid itself seem to play little or no role, and because the tip of the tongue has none of the distinctive hair-like rough projections that make cats' tongues feel so distinctive, they also play no part in the physics of lapping. It also seems that cats drink in a very, very different way to dogs, who merely use their tongues to scoop up liquid like a ladle. Now, as well as helping us to understand how cats maintain their refined image, even when lapping rainwater out of a puddle, understanding these mechanisms will inform biomechanical models and will help us to design better soft robots. You're listening to The Naked Scientists with Ben Valsler and with Helen Scales. Now, hello to everybody listening in Second Life. We've had a question from J.S. Euralia based on the fact that we were talking about geological periods earlier. He's asked if the Cambrian period is named after Cambridge. Very good question, and I must admit I did have to look it up. But no, it's actually named after the Latin name for Wales, which is Cambria. And that's because there are Welsh mountains where we see some of the best examples of these rocks. So thank you ever so much for your question.
Well, when American scientists discovered some tree fossils in 2007, they turned out to be 385 million years old. That makes them among the world's oldest trees. But in order to identify these trees, they needed help of fossil tree expert Dr. Christopher Berry from Cardiff University. Well, Christopher travels the world, very great job, searching for ancient tree and plant fossils and analyses them back in his lab. Planet Earth podcast presenter Sue Nelson joined him at the university's School of Earth and Ocean Sciences to see some of these fossils for herself.
So this is a paleontology laboratory.
Oh, lovely squeaky door. And is that I hope that's not a priceless fossil you're using as a doorstop there.
That's used to be a priceless fossil from Venezuela, but now I've chopped the fossil off it, so it's just a block of rock.
Good. Well, let's see some of the blocks of rock that you've got here in your laboratory.
On the bench we have some slabs of dark grey mudstone, and on those slabs we have some impressions and compressions of fossil trees. The compressions are of the branches of these fossil trees.
It's not that easy to see, though. I mean, you're saying that, and I can see where the central one is, but it's harder to actually distinguish the bits you're looking for. Anna, you've just picked up a jar of liquid here.
Yes, this is alcohol, and one of the ways we can see these fossils better is just by simply pouring some of the liquid onto the fossil.
Oh, yes.
And there you can see that the contrast between the fossil itself, made out of carbon, and the dark grey rock becomes enhanced.
You can actually see what looks like a very feathery frond branch, about sort of the length of my finger. And what plant was this, and when was this plant on the Earth?
The name of the plant is Archaeopteris. It's technically called a progymnosperm, but this simply means it's related to the living conifers, and it was alive at the boundary between the Middle and Upper Devonian, and that means 485 million years ago.
So what can you learn from a large fossil like this?
What I'm particularly interested in is the morphology of the plant, that's to say its shape, its form and its size. And these fossils are particularly important because they tell us a bit about the size of a tree. If we're interested in the impact of trees on the environment, the amount of carbon in a plant is probably one of the most important things, as well as the size of its rooting system.
Well, let's move across your laboratory now to another bench table where next to a microscope you've got a sequence of rocks that you've laid out for me, each one imprinted with rather beautiful stems, branches of ancient plants.
Yes, these are more of the same type of plant. They're slightly younger. It is very similar in shape to a fern frond, but it's actually a branch of one of these early trees. And because it's a branch, it's much more woody. It would be much more stiff and not as floppy as a fern frond. But the structure is the same. You have a long central axis, little branches coming off the side on each side of that, forming a large sort of flattened structure. And then attached to those little branches are little leaves.
Moving along then, how does this differ? Because the rocks towards the right-hand side are quite different in terms of their fossils, because those ones look as though they have roundish or heart-shaped leaves.
That's right. As we come up through time, the leaves of these plants become less wedge-shaped and more full. They've got a margin which goes right around the outside with no incisions in it. And the things become more flattened, if you like, more webbed and more photosynthetically efficient.
What importance is it in terms of the Earth today, knowing how our ancient forests were?
We know today that there's a tremendous difference between environments in which there are natural forests and environments today where those forests have been stripped away and you're left with bare earth. Think of a rainforest. If you strip down the rainforest, then the soil that the trees have been growing in is very quickly washed away. There are very important things going on in the soils beneath the plants, caused by the roots, the fungi in the roots, and the interaction of these roots with the minerals in which they're growing. These are very important processes. They not only control what the soil is like, but in fact they actually draw down gases from the atmosphere, particularly carbon dioxide, and take that carbon dioxide out of the atmosphere and transport it away so it's deposited as solid minerals within the sea. And this is an incredibly important process. We all know about the problems of carbon dioxide in the atmosphere today. This is one of the ways in which carbon dioxide was removed from the atmosphere in the past.
Fossil tree expert Christopher Berry explaining the importance of ancient trees to Planet Earth podcast presenter Sue Nelson. And you can hear a longer version of that interview and download the latest podcast both from our website and the Planet Earth online website.
Now, we are talking about the science of shipping this week. Your questions are coming in, so we'll try and get through some of those later on. But now it's time to set sail and join Mira and Dave, who are making some waves.
This week on Naked Engineering, Dave and I are sticking with the theme of shipping, but we're going to look into a few of the basics and see just how ships actually float and what forces are acting on them when they're out at sea. Now, Dave, firstly, how does a ship float?
Well, water is quite heavy stuff. It weighs about a kilogram for every litre or a tonne for every cubic metre. This means that the deeper you go, the higher the pressure is. So the water pressure at the bottom of the ship is going to be a lot higher than the top, which means that overall there's a net force pushing it up and you get this upthrust force which holds up the boat.
What actually happens then to a boat or a ship out at sea? What sort of forces act on it and how is this overcome to keep it afloat?
Well, there's two major forces, of course. There's the upthrust and gravity. Gravity pulls it down, and some bits of the ship are heavier than others, so they're going to have more gravity associated with them. And other places are going to have more upthrust than weight, so they like being lifted up. The actual sort of structural design of a ship is all about transferring the forces from the upthrust to where all the weight is to hold everything up and keep it nice and stable. Even naturally with the ship just lying in the sea in perfectly calm waters, there are quite big stresses in it. It's like you've got heavy engines in one place, and also the bow and stern, the ends of the ship sink downwards, which is called hogging.
These forces are obviously important to understand, but especially on a damaged ship to see just what might happen if a ship were damaged out at sea. So to find out a bit more about this, we've come along to the Fluids Laboratory at University College London to meet Daniel Phone, who looks into just this.
I'm looking into damaged ships, and more specifically damaged ships in waves. The majority of the research that's been done is on a ship in still water.
And I guess waves put a very large stress on a ship, and if you have a damaged ship, the time you're really, really worried is if you're in the middle of a big storm.
Precisely, and when a ship is damaged, it's got less structure to withstand that stress.
Well, we've come along to your lab to see where you actually conduct your research, and now there's a gigantic water tank in front of us. It's 20 metres long, 2.5 metres wide. It's filled with water about a metre deep, with a model of a ship just floating along in the middle.
This tank has two capabilities. Firstly, it has a wave maker at one end, which can generate really accurate deep water waves. And the second is there's a towing rail which spans the length of the tank. We can attach models to it.
And so in the middle of this tank, though, you do have a 2-metre model of a ship, but it's kind of pieced together. What's going on here? What are you actually looking into on this ship?
So we call this experiment the hinged ship experiment. We've taken a 2-metre long model, cut it completely in half, and then hinged the two halves back together. We've also positioned load cells, which are little devices that can measure a force experienced as a result of waves passing the model. The most critical loading case of a ship, even when it's not damaged, is when it bends longitudinally. So as Dave's previously mentioned, a ship tends to bend along its length, so the front and back, or bow and stern, dip into the water if there's less buoyancy, or they can come out of the water more than the middle, and so you get a bending effect of the ship. And this is what our experiment is principally set up to capture. And we want to know the effect of damage, its location, the size of the hole on that force.
So what kind of damage are you actually inducing then?
Well, this model is made out of PVC and plywood. And the good thing about that is we can easily drill holes in the bottom of it and then patch them up, so we can move the damage around as and when we please almost. The way that this experiment's set up, we're looking at symmetrical damage, symmetrical about the centre line of the model, which is a good simplistic representation of a ship being grounded. I mean, if you think about the number of variables there are to consider when a ship does get damaged, the size of the damage, the shape of the hull, the roughness of the hull, where it is along the length of the ship, whether it's at the kind of waterline on one side or whether it's along the bottom, and the compartment that it's damaging, is it full of equipment and machinery or is it an empty cargo tank? All of these things have quite a significant impact on the forces that are going to result from the damage.
So we have got this giant water tank in front of us. Could we see this in action?
Of course. So I'm going to make a variety of different wavelengths, and we have a screen here which will give us readings for the forces in the middle of the ship and also the motion of the front and end. We've instructed the wavemaker in this case to generate what's known as regular waves, so sinusoidal in nature.
So you've got a nice string of waves with a wavelength of about 1 metre.
And now looking at the screen showing all of the forces acting on the ship then, what's happening to the model of the ship?
So the model is being excited by these passing waves, and we have sensors positioned to measure displacement at the front and the back. We also have our load cells that we previously talked about, giving out readings of a force, and we have a series of wave probes which measure the displacement of the water wherever they're mounted. So the model here is exhibiting bending, as can be seen by the screen. It's also obviously moving up and down as the waves go past, and the water inside is moving up and down relative to the model as well.
I've been having a look at the screen and it seems to be using quite arbitrary units of force, but at the moment the force seems to be about 0.3 units peak to peak.
OK, and Daniel, you're now changing the wavelength and making it slightly longer.
So I've now reduced the frequency of the wave, meaning that the wave length will be longer, and we're going to see what happens when the wave length is exactly the same as the ship length.
The forces have all seemed to change on the actual graphical screen.
Well, the waves that we have passing the model now, their length is equal to the length of the model. And this, in kind of classical ship theory, is known to be the worst case of bending on a ship. These waves, if you were to freeze them as they were passing the model, you'd find that because they're of the same length as the ship, you'd have a peak at either end and a trough in the middle.
Which means there's no support in the middle.
Exactly, there's no buoyancy in the middle, but there's a maximum buoyancy at either end, so the model will bend.
OK, so we've seen that there are clear differences when there are different wavelengths and different kind of factors affecting a ship. What have you managed to find to date, Daniel?
Well, a lot of the software at the moment that models ships that are damaged generally don't take account to the fact that there's a hole in the ship. They fill a tank full of water but don't have any hole in it. We simulated the same scenario with our model, and we also then compared it with the case where there's a hole in the same compartment, and we found that the behaviour of the fluid inside the model was incredibly different. The case without a hole results in very violent floodwater motion, whereas the same scenario but with a hole in it, there's a very well-behaved floodwater motion. The fact that there's actually a hole there has a kind of damping effect.
How can all of this be used to actually help captains when they're out at sea with a damaged ship?
Well, ourselves and the University of Southampton are developing a series of computer tools that can model a ship that's damaged in waves. And these experiments are principally being carried out to validate any results that their and our software are producing. And this software, we hope in the future, will be able to assist captains out at sea when they get into an emergency response scenario, when they report what kind of damage has occurred. We're hoping our software will be able to tell the captain whether he should stay put, given the weather forecast, whether he can make it back under his own steam to a safe haven, or whether he needs to be towed, or whether to completely jump ship, get out of there because it's going to break in half.
I'm sure all captains out at sea would be very grateful to be forewarned that their ship is about to split in half. That was Daniel Phone from University College London talking to Mira and Dave. Naked Engineering is supported by an ingenious grant from the Royal Academy of Engineering, and if you'd like to see their wave tank in action, then you can find a video of Mira and Dave's engineering adventures at thenakedscientists.com/engineering.
Well, continuing with the shipping theme, we're joined by another UCL researcher now, Tristan Smith, who's looking at ways of making shipping more sustainable. Hi, Tristan.
Hi there.
Thanks for joining us. We generally think about air freight as being the eco-villain when it comes to transporting things, including people, around the world, but shipping actually isn't environmentally innocent, is it? How do those emissions from planes and ships actually compare?
OK, so if we look at a sort of global level, then shipping has got a very similar magnitude global emission of carbon dioxide to the aviation sector. Overall, it's about the same. The difference is the amount of stuff that we move by ship is many, many more times greater. So ships are by themselves quite efficient carriers of cargo, but there are a lot of them in the world, and so they're still a significant issue in the carbon discussions that are going on.
And that's the carbon discussion specifically, so we're talking about climate change, but it's not just carbon that we should really be thinking about when it comes to shipping transport, is it? We've also got other nasties coming out of shipping fuel as well, including sulphur is a big problem.
That's quite right. Historically, ships haven't had the most highly regulated ways of being operated, and so we're still burning fuels in ships which were outlawed on land many, many years ago. And at the moment, that means that we're still burning very high sulphur fuels, ones with percentages of sulphur in their emission of about 3.5–4% in some cases. And that means that there are significant health issues associated with that.
So there are health issues associated with sulphur. Am I right that actually it counteracts climate change to some extent? When the sulphur in the atmosphere, it helps reflect heat back into space?
That's great. Well, I'm not a climate scientist expert,
okay.
But I have heard that this is true, that there's a radiative forcing effect associated with the sulphur emission, which means that you actually get a cooling. But that is a very short-term effect, so the sulphur is very quickly broken down in the atmosphere, and we can't really think of it as being the same effect as the one associated with the carbon emission, which obviously hangs around in the air for a lot longer.
OK, so we've got these sort of slightly dirty fuels being used in the shipping industry, and that overall, we've got the same amount of carbon coming out as we do from aeroplanes, but we're moving in a lot more stuff around the world. In terms of trying to make shipping more sustainable, where are you targeting your efforts? Are you looking at fuel, or is it also about the boat designs as well themselves?
I think it's got to be a consideration of everything. It's actually quite an expensive sector to decarbonise because, as many people are aware, we've been building ships and moving stuff in them for a very long time, and we've got very efficient and good at it. But that doesn't mean that there isn't more that can be done. So certainly technologies that go on the ship itself, whether that's an engine modification or a means of assisting its propulsion in some way, such as a renewable technology. And then the fuels are something that you can do something about as well. You can move perhaps to liquid natural gas fuel, which is being talked about at the moment, or even biofuels or hydrogen at some point in the future, perhaps.
And there is, to some extent, the fact that that shipping fuels are sort of under the radar a bit, and that we're not really thinking about them. We've actually had a question come in from Dally Waverider, who says that, in my understanding, is that basically marine fuel is asphalt, the dregs of the oil refinery process, but that the real problem is that this all happens out at sea and there's no one really to complain about it, and wants to know if there is any moves underway to burn cleaner fuels at sea. So why is it that we aren't really regulating what's going on in terms of shipping emissions and fuels being used?
Well, I think it's partly that. It's out at sea, it's out of sight, it's out of mind, and so quite often doesn't get the clamour of public opinion that might drive changes in other industries. It's also a very international industry, and so it's regulation is very hard to bring in because you might change something in Europe, but in practice everyone might fill their ships up in a different continent. So it's very hard to bring something in that's going to be universally effective. But there is currently a regulation due to come into force in 2020, which will mean that we can no longer burn the sort of heavy fuel oils, which is the generic term for the high sulfur fuels that are currently being burnt on ships.
And there are some other environmental impacts of shipping as well, aren't there? I mean, one thing I suppose to consider is the issues of ballast water and carrying various species around the oceans that aren't supposed to be there. That presumably is something else that needs to be thought about.
Quite. It's one of those unintended consequences that just all of a sudden someone points out and you think, well, why didn't we think of that before? Unfortunately, when a ship has discharged its cargo, it needs to take on water in order to make sure that when it goes back out to sea, it will be stable enough not to capsize. And that water is pumped into the ship when it is in its port at which it's just offloaded its goods. And then as it moves across the oceans and comes to another part of the world, it will then pump out the water. And that's been a very neat way of moving one species from one part of the world to another that probably wouldn't have got there under its own steam.
Absolutely. So that's something that needs to be considered. But if we head back to the boats again, is there, we've been using boats, like you said, for probably as long as we've been moving ourselves around the world. But can we radically redesign the way boats are made and the way we do travel across the oceans? Is there some way that we can sort of rethink the whole thing to make it even more sustainable today?
Absolutely, and I think there's a myriad of brilliant ideas out there that could all be fantastic solutions in the future to help tackle climate change and to make shipping a much more environmentally friendly means of moving goods and make it the most environmentally friendly and more competitive than the alternative modes. But they all need to be thought through in terms of the detailed design, but also their economics, because everything comes at a price and some things are going to be cheaper than others.
And just to throw an enormous question out at you, what would you think the ideal situation would be if we were looking forwards into the future of global container shipping and moving things around the world? What would be the best thing that we could look forward to, do you think?
Well, I'm quite a big fan of wind power as a means of supporting some other onboard fuel that could be used to take up and keep the ship on schedule if the wind suddenly dies. So, for example, a hydrogen-powered fuel cell or a biofuel-powered, very efficient diesel engine could be a means of providing a combination of technologies that could deliver that very efficient, low-carbon ship in the future.
So we could be looking at almost a sort of hybrid between a sailing ship and a cutting-edge 21st century battery-powered ship to get us around the oceans, maybe?
I think it's a combination. There's nothing that's going to beat the fantastic efficiency, or not efficiency, but economic efficiency of a fuel like oil and a diesel engine, but it's going to be a combination of things that comes in to do something similar.
Fantastic. Well, thanks, Tristan. That was Tristan Smith. He's from University College London, and he'll actually be with us for the rest of the show. So if you've got any questions you'd like him to have a go at, or for us, then do get in touch. We are at Naked Oceans. Alternative, you can write it on our Facebook wall, thenakedscientist.com/Facebook. I just said oceans, I meant Naked Scientists. Sorry. There we go. Just dropping something else in there. But do send us an email, chris@thenakedscientist.com.
Slight Freudian slip there. You can get more information about what's going on in the oceans in the Naked Oceans podcast. That's at Naked Oceans on Twitter. But if you'd like to get in touch with us, tweet at Naked Scientists.
Keeping you abreast of the world's best science. The Naked Scientists.
This is The Naked Scientists with me, Ben Valsler, and with Helen Scales.
Still to come, Diana finds out if a big enough ball of bees could boil a human in our question of the week.
But first, we are talking about sustainable shipping today, and one idea put forward has been to find ways to harness the power of the wind in its rather traditional role of filling some sails. Now, I spoke to Stefan Brabeck from the German company SkySails.
We started to develop SkySails because we could see that the oil price will rise, and also the nature has to be saved more and more. And we thought about to find a solution to propel ships with alternatives than just the main propulsion depending on fuel. So there, the idea came up. We looked to the kite surfer, how much power they generate with this small kitesurf kites, and we asked us how to transform this technology to big ships.
Because, of course, wind power is one of the oldest ways that we've powered ships in the entirety of human history.
Yes, but the former sailing ships came out of attention because fuel was so cheap on one side, and on the other side, nowadays the ship we have a clear deck to load and unload, so you cannot afford masts to bear the sails. And so we came to the idea to have a system which is you can store away during unloading and loading of a ship.
How have you developed that idea to build a skysail? What physically is the skysail?
Yeah, the skysail is parafoil, which is attached by a rope to a ship. We use a parafoil instead of a kite. It's filled with air, and so we fly a profile through the air, and the profile has much more lift than a single sheet of cloth. And that was the idea, to use these parafoils to generate high thrust, which is possible that we tow a ship by minimum 50 to 60% of the main propulsion.
So this parafoil design, it's essentially a series of chambers in the cloth rather than just a sheet of cloth, and that gives you much better performance.
Yes, that's correct. The cloth itself of this parafoil is like sailcloth, a little bit reinforced against UV radiation, and also at the line attachment points where we have to transmit this high load to the rope and to the ship.
So you obviously have to reinforce it if you're putting that much force through. The rope itself, can you just use traditional sailing rope, or does that also have to be reinforced?
The rope itself is a very modern material. It has about 10% of the weight of a steel rope of the same strength. And on the other side, it is very durable, made from Dyneema. That's a very new fiber and very strong fiber. And the real challenge was to introduce into the rope a cable, because you can imagine that we have to steer this kite, and for the steering purposes we have a small control pod between the kite and the rope, and there are some computers in and also an electric motor to control the kite, and this motor needs energy, and so we had to include into the rope cable, and that was also special development.
And what altitude do they actually fly at? Presumably higher than a conventional sail would be able to.
Yes, we fly the system between a height between 100 and 300 meters. In this height, we have about 25 to 30% more wind than close to the surface of the water, due to the circumstance that we have left the boundary layer of the Earth's surface at about 100 meters. There we have the full wind, so we have about 25 to 30% more wind force there.
What conditions can you fly it in? Does it need to be perfect weather? Does the wind have to be going in exactly the right direction? Or are there tricks that you can employ to use them in not so great weather, or when the wind's going on a bit of a tangent?
We use about 180 degree the wind, like a sailing boat, so we can also even go a little bit against the wind and to keep the system flying. But the most profitable course is from 90 degree to 270 degree downwind and reaching wind. And if we have more and stronger winds, even we don't start, or we can also leave the system at the heaven in static condition. So the captain has not to care about to leave the system just flying, but without making figures to generate power.
You don't just deploy the kite and allow that to pull it along. You actually have to make these weaving patterns to get more power out. How does that work?
The kite will be moved, or is moving with a velocity of about 50 miles per hour to 150 miles per hour. And the kite will be maneuvered in kind of a figure 8 in front of the ship. And the lift of a parafoil is growing by square with the velocity of the wind. And that is the reason why we can generate with such a small surface such a high thrust. There are sailing vessels of about 100 meter length with close of 3,000 square meter. We can generate the same thrust with about 160 to 200 square meter.
What sort of difference does that actually make to fuel usage?
On a small ship, about 4,000 tons, about 90 meter long, there we can save about 1 to 1.5 ton per day at sea with this system in average. So we have not every day the condition to use the system, but if we use the system, then the savings are very high, up to 50-60%. Such a ship consumes about 6 tons of fuel per day. If we are working, we save about 3 tons per day, but in average over the year, it's 1 to 1.5 ton per day. So over the year, 300 tons, and that means 90,000 to 120,000 euro savings per year for the customer, for the owner. And on the other side, for the ecological side, we save between 600 and 900 tons of carbon per year.
That was Stefan Brabeck. He's the technical director of SkySails. And I think that's a fantastic idea and such a simple one. And if you've ever had a go at power kiting or kite surfing or anything like that, you'll be aware of quite how much power some fairly small kites actually have. Helen, you spend an awful lot of time on the seashore and so on. Ever tried kite surfing?
I've never tried it, but I've seen it happening and sort of felt tempted. But it looks pretty scary when the people get whisked like a long way off the surface of the sea by these enormous sails. And they're reasonably big, but you're right, they generate a huge amount of lift and pretty powerful stuff. So yeah, great idea.
Well, the parafoil idea is incredibly simple. In fact, it's probably something Dave and I should do in a kitchen science at some point, because I've got a parafoil kite that's not really any bigger than a sheet of A4, and it flies in very, very little wind. But we've had a question here, Helen, that I think is probably a good one for you, from Ellie. She wants to know if there are any health risks associated with eating fish. In particular, she's talking about tuna and salmon, but there might be other ones.
Right. Well, there is talk about various nasties that you might get in predatory fish like tuna from the open ocean. They will end up potentially having quite high levels of things like mercury in their flesh, which is one reason why you're not recommended to eat it perhaps more than once a week. But, you know, there's various different levels on that. So there are things that end up in tuna. Farmed salmon as well might have some various aspects of the way it was reared that's going to end up in it when you eat it. But actually, I think some of the more interesting things about what's bad about eating fish are things like puffer fish. They're great. You have to prepare those absolutely right. Otherwise, a toxin in some of their organs called tetradon toxin will actually knock you off and kill you. But the interesting thing is that people have worked out a way of farming these fish without any of this toxin anymore. So they're perfectly safe. But nobody wants to buy them. There is no market for safe puffer fish because it's all about the risk and the tingling of the lips when you've just got a little bit of toxin, just to make you know that you're a macho fish eater and that you're taking your life in your own hands and trusting the chef, because it's all down to a very skillful removal of those innards that are otherwise deadly.
So people possibly eat these sorts of fish for the same reason that they go kite surfing, just for that
so.
adrenaline rush
Thrill.
of being close to death. This is The Naked Scientists. Today we're looking at the science of sustainable shipping. We have Tristan Smith with us from UCL. Tristan, we've had a couple of questions come in. One from Skychild at Twitter, which is very nice of him, and one from Simon McCarthy. That was an email. And they're both related, really. Skychild asks if there are any other means of propulsion other than a propeller. And Simon McCarthy is basically saying if impellers are more efficient than propellers, are they? And if they are, then why don't we use those on boats instead? What do you think?
Right, so there are some other types of propulsor than propellers, and ducted propulsors are one of them, which I think the second question is referring to. But if we just start with a few of the other propulsors first, we've got water jets, which are used on very fast ships, and they're a bit like a pump that pumps water in from the sea and then it expels it at high speed out of the back of the ship. And you often see them on the back of catamarans that you might take across the channel to go to France. So those are good if you're travelling very fast. And another one that's worth mentioning is some flapping paddles. So people have actually experimented over the years to try and recreate the motion of a whale's tail in order to propel a ship along, to see if that might be any more efficient than the propeller that you typically have on the back of a ship. At the moment, no one's come up with something which is as robust or as efficient as the propeller, or reliably efficient as the existing propeller.
Of course, when you're actually swimming for yourself in the sea, there are some wonderful devices. You get these enormous monofins, which I believe, Helen, you've had a play with recently.
I have. They're so much fun. So I was thinking a whale ship just sounds brilliant. But no, swimming with a monofin is a very powerful way of a human getting themselves through the water. Yeah, that sounds like it is a lot of fun. You should try it out. We've also heard from David Worley on Twitter, who's wondering whether we're getting anywhere near to having robotic unmanned cargo ships.
So I think this would be a good thing as long as you weren't a ship's captain or a crewman. But I think there's a lot of electronics that could be done, and the technology is probably feasible, but the legal implications of having unmanned ships sailing around the world are probably a bit tricky to sort out. If you have an accident, who's going to try and remedy the situation or salvage anything? And how do you avoid the collision in the first place? Can you actually make sure that the ship's computers are going to be reliable enough in order to stop that? So there are lots of detailed practical issues, but certainly the technology could be there, and it's something that there are researchers who are working quite hard to achieve, exploring at the moment.
I would imagine there were lots of companies who still won't really trust all of that cargo to a robotic machine. Instead, they really want something that they know there's a man in charge. Although I'd imagine human error is actually quite a big problem. We've had a question just lastly for you from John in Colchester. He said, if we didn't burn this thick, sulphurous diesel in the marine engines that we've got, what could we actually do with it?
I think that's a really good question. I mean, we could build more roads, I suppose, but that doesn't really sound like a very good thing to do. So what the refinery would actually do with this byproduct of the refining process of a heavy crude is not particularly clear, and I think it's something that they would probably have concerns about too. Who's actually going to take the stuff off their hands if the ships aren't consuming it themselves? The ships are basically the last industry that's still using it as a fuel, and there are no sort of major takers left in the world at the moment.
Thank you very much, Tristan. That's Tristan Smith from UCL. And now it's time to join Diana O'Carroll, who's the queen bee of our question of the week.
This week, what be the problem?
Hello, I'm Jane from Cambridge, and I have a question for you. Out of interest, having just discovered that when bees are attacked by something like a hornet, they can form a bee ball around it and boil it to death with all the heat generated in this ball, I was wondering whether it's theoretically possible that they could do the same to a human. Given unlimited bees, I suppose. I wonder how many you'd need.
So first of all, what's happening when the bees do the boiling?
My name is Jürgen Tautz. I'm working in the university at Würzburg in Germany, and I'm heading the bee group. The heat by the honeybee is produced by its strongest machine, which is the wing muscles used for flight activity usually. So the bees can mechanically decouple their wings and let the flight muscles run full power. And this way a lot of heat is being produced, which gets to about 65 millijoule if one takes the energy. The energy for producing this heat is taken then by the honey. So the honey, which the bees are producing from the nectar they collect at flowers, this is the source of energy they have to eat first and then transform it into heat.
And how many bees would have to feast on honey before decoupling their wings?
The calculation can go like this. So if we assume that a human consists of about 50 liters of pure water, which is close to realistic, that a human dies at 42 centigrade, which means a human has to be heated up from 36 to 42 centigrade. We need to heat up 1 gram of water, so 1 milliliter of water. For 1 degree Celsius, we need 5 joule, which means to heat up a human for 6 centigrade, we need 1.5 million joule. If, on the other hand, we take the heat which can be produced by a honeybee, which is 65 millijoule, it's very easy now to calculate how many bees we need to heat a human to death which is roughly about 20 million honeybees, which comes close to about 1,000 mid-sized bee colonies. So not much space on the surface of a human to give access to all these bees.
That's right, 20 million bees or 1,000 colonies to essentially cook a human. And to heat a person up to 100 degrees, roughly the boiling point of water, you'd need about 250 million bees. That's 12,500 colonies, or about a sixth of all the hives currently registered in the UK. But you'd only need to feed them 160 million joules worth of honey, which you'd find in about 50 jars of the stuff, and that honey would cost you about 150 quid, which isn't so bad. Speaking of insects...
Hello, this is Silva from Vienna in Austria. I was wondering what exactly happens when a caterpillar pupates and then turns into a butterfly. Does it liquefy into some sort of protein sludge and start from scratch, or does it just grow wings? Thank you, bye.
What happens behind the closed doors of a chrysalis? Answers on our forum at thenakedscientists.com/forum, or email us with the address, and that's chris@thenakedscientists.com.
Thank you, Diana. So if you know what's going on in a caterpillar's metamorphosis, then do get in touch. Drop us an email to chris@thenakedscientists.com with your ideas. That's all we have time for this week. Next week, Chris will be back with Sarah Castor-Perry to look at cognition-enhancing, or so-called smart drugs. We'll be asking if they really work to give you a brain boost, and if universities should be dope testing before exams, much like they do athletes in the Olympics. If you've got any questions or comments on that or any other science topic, get them into us by email to chris@thenakedscientists.com, or through Twitter, tweet @Naked Scientists. Many thanks to John Parnell, Stefan Brabeck and Tristan Smith for joining us this week, and to our production team Tom Simpkins, Mira Senthalingam, Dave Ansell and Diana O'Carroll. Thanks for listening, and goodbye.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at thenakedscientists.com.